Welcome back. Chapter 2, Section 2.1. How to find a solution curve without actually finding a solution. Sometimes you're unable to solve a differential equation exactly for a numeric, like a functional solution, right? You can't always find the function y equal to some function of x. But with the help of computers, honestly, you can find solution curves in some cases. So let's think about the setup here. So we've got a first order ordinary differential equation, and it's written in a very specific form, right? On the left-hand side, we've got dy dx by itself. So this is a first order differential equation, which means the highest derivative order is 1. And we're going to put dy dx by itself with a coefficient of 1 on the left-hand side. Then on the right-hand side, we're going to have some function f, which is a function of x, the independent variable, and the dependent variable y, but no derivatives of y. So this on the right-hand side is just a function of x and y, and the single derivative is over here on the left-hand side. And let's assume that we cannot find a solution to this differential equation for the moment. Well, in that case, we can still do quite a lot to visualize what the solutions look like, because it's in this very special form. Let me explain. Here is one method, direction fields. If we were to have a solution to this differential equation, it must be the case that this function y is differentiable on its interval. By virtue of solving a differential equation, a function has to be differentiable. That's like step 1. In order to even be a candidate for a solution to a differential equation with a derivative in it, you have to be a differentiable function on this interval I, whatever this interval is. More importantly, since this is differentiable, we can find a slope of this function y of x. And what is the slope of a function y of x? Well, it's the derivative of y with respect to x, right? That's an expression for the slope of this function. And if we look at our differential equation, we can see this on the left-hand side, this is the slope of y. This is the slope of y, and it's equal to this function f of x and y. So while we might not be able to find a solution y, we can say what the slope of this solution is at every point, because it's given by this this function. So f of x and y is the slope of y of x at all points, x comma y. It'll make more sense when we draw it out. But that is the intuition. And here it is written down in words, right? More importantly, the slope of the solution at every point x in the interval is given by this function f of x and whatever the value of y is associated to that x. Since the slope of y of x is equal to the derivative of y with respect to x, which is equal to this function f of x and y. In order to visualize this, we're going to draw what we call a direction field. It's much easier to do by example than it is to explain what a direction field is, but I'll do it in words really quickly. A direction field is basically a graph, and at every point in the plane you put a little arrow or a line segment which represents the slope of the solutions at that point in the plane. So you start with the empty plane, and then at every point you add little line segments or little arrows, right, showing how the solution is moving through space. That's the idea. Let's do an example. Here's a differential equation, a first order differential equation. Now, we don't know how to solve it yet. We'll learn in the next section how to solve these kinds of differential equations, but this is actually what's going to be called a separable. Oh, my handwriting's so bad. Separable differential equation. And we can solve this exactly. We don't have to draw the direction field for this guy. But for the sake of this example, we're going to draw the direction field because right now we don't know how to solve a differential equation. Let's remember that in order to draw a direction field, we need the setup to be dy dx on the left-hand side by itself, coefficient of 1. Looks good. And on the right-hand side, this over here is f. This is f of x and y. Right, this is our function of x and y. So let's imagine what's going on here, right? At every point x comma y, we can plug in that pair, x comma y, into this function f, and that will give us the slope of the solution at that point. The slope of the solution at that point. So how do we do this? Well, we're going to pick some points, x, y in the plane, and we're going to find the slope at that point using this function, f of x and y. Once we do that, we're going to draw, just like I said, little line segments, right? Little line segments that represent, the direction of the slope at every point. Here's an example. Well, this is not an example. This is the same example, right? Using this function, 0.2 x comma y. Here's the direction field. Now, you can see the little arrows or the line segments I was talking about, but how do we get these values? Okay, let's take a point in the second quadrant, right? Let's take the point x comma y equals -2, 2, right? That's this point here. And let's plug that into f, right? So f of -2, 2 is going to equal 0.2 times -2 times 2, which is equal to, what is that equal to? That's -4 times 0.2, which is -0.8. Right, this is -0.8. And that's supposed to be equal to dy dx. That's the slope at that point, right? So what do? We go to the point -2 comma 2, and we draw a little line segment that has slope -0.8. Right, we go to the point -2, 2 in the plane, and we draw a little line segment or a little arrow that has the slope -0.8. And if we look, that looks about like this guy here. Right, it's close to a -1 slope. It's close to a -1 slope. It's not exactly a -1 slope, but it's pretty close, right? And then sometimes, it depends on how lazy I'm being. Sometimes I'll, like down here, I'll just do a little line segment, and sometimes I'll actually do a little line segment with the arrow tip on it. And to me, this is supposed to be like a flow. This is kind of like a flow chart, right? So you can imagine, right? You can imagine if I were to try to pick out a solution passing through a specific point, right? Let's say I want my solution to pass through this point, -2, 2. Let's say I add some initial condition onto my differential equation that says that the solution must pass through -2, 2. Well, how does my solution look? Right? How does my solution look? In order to figure that out, we just have to follow the flow of the direction field. Right? So if I imagine like following the flow of the direction field, I can draw out what my solution will look like. Does that make sense? We can start at the point -2, 2, and follow the flow of the direction field to see the shape of the function. That is the solution. Now, if I pick a different initial point, let's say I pick a point down here, right? Let's say I pick this point right here on the excuse me. I pick a point right here on the y-axis. 0, -2. All I need to do is follow the flow of the direction field. That was kind of bad. Follow the flow of the direction field, right? And that is my sketch of a solution curve passing through this point, 0, -2. And on the next page here, I've done a few examples of this, right? So the idea is they give you the differential equation without any initial conditions, right? No initial conditions. No initial conditions on this guy. But this characterizes, there are infinitely many solutions to this, is the idea. There are infinitely many solutions to this. The way we can pin one of them down is by adding an initial condition. Adding an initial condition. So if I pick the initial condition that y of 0 equals 1, right, this red condition up here, y of 0 equals 1, that means my solution y goes through the point 0, 1. That means my solution goes through the point 0, 1. So how do I find what that solution looks like given this initial condition? I put my finger on the point 0, 1, and then I follow the flow of the direction field. Follow the flow of the direction field. Same thing with this one down here. Y of 0 equals -1/3. I put my finger on 0, -1/3, and I follow the flow of the direction field. Y of 0 equals 0, same thing. Put my finger right here, and I follow the flow of the direction field. Now, how do I know what the solution looks like? These little line segments are supposed to be the slope of the curve at that point. The slope of the curve at that point, which means my solution curve is tangent to all of these little line segments. Just like in Calculus 1, right? When you draw like a little tangent line, right? If I were to extend out the tangent line at this point, it would look something like this. Just like one of the arrows in the field. Same slope as one of the little arrows right here, right? So all of these line segments are supposed to be tangent to my solution curves, which means I can just make sure that I'm tangent to the direction field at every point. And if I ensure that I'm tangent to the direction field at all points, this is the solution curve, as long as it passes through the specified point. So this is a little bit about how direction fields can help us visualize the solutions to a differential equation without actually solving the differential equation. They're pretty useful, but again, hard to do by hand, easy to do on the computer. Right? Easy to do on the computer. Here's a similar method. Same setup, right? We've got dy dx equals f of x and y. That's our differential equation. And instead of picking points at random and drawing little line segments, you can do what's called the method of isoclines. And if you remember, well, I guess not remember, but if you know a little bit about breaking words down that have, I guess, Latin origins, I don't know. I'm not a linguist. The word iso is used in like isosceles triangles and isomorphic, right? It means same, right? Isocline means same slope. That's what isocline translates to, kind of. Right? This is the method of same slopes. The idea here is we're going to set f equal to a constant. And remember that f is equal to the slope. So essentially what we're doing when we set f equal to a constant is we're setting the slope equal to a constant. And we're going to find a function y of x involving c where the slopes are all the same. So let's take the same example from before, right? So if you remember the example from above, it was dy dx equals 0.2xy. That was our differential equation. And we're going to set 0.2xy equal to a constant. Set 0.2xy equal to a constant. Now, we can solve this equation for y, right? Solve for y. And we get y equals 5c over x. And at this point, it's key to remember that choosing values of c is choosing the slope along some isocline. And that isocline, right, these are the isoclines. They're given by these functions for different values of c. Now, the picture that's coming up is going to be a little bit overwhelming, but we're going to try to walk through it, okay? Here we go. What happens? Okay, I'm going to choose c equals 0. Right, I'm going to pick c equals 0. In this case, if I pick c equals 0, then I get y equals 0 as my isocline. And along the line y equals 0 and also x equals 0, the slope of the tangent lines are 0. Right? I picked the constant equal to 0, which remember is supposed to be equal to the slope. Right, this equals the slope. So if I pick c equals 0, I'm saying slope equals 0. Slope equals 0. And where does the slope equal 0? Along the line y equals 0 and also x equals 0. So I go over to my graph. And I look for the line y equals 0. That's this line right down here. That's the x-axis. That's the line y equals 0. All along this line, the slope of the tangent lines, right, the slope of the direction field line should be 0. So I go along and I add little 0 slope indicators all along the x-axis. And then I also do it for x equals 0, right? All along the x-axis, the slope of these little line segments is 0. Right? 0 slope, 0 slope, 0 slope, 0 slope, 0 slope, 0 slope, all the way down. That's a single isocline. What about if I pick c equals 1? So now I'm saying slope equals 1. Where does the slope equal 1? Well, if I go back up, these are my isoclines. When I plug in c equals 1, I get y equals 5 over x. Y equals 5 over x. If you remember what this looks like, this is a little curve like this. Right? The 1 over x curves look something like this. So I go and I find my little curves. It's these two right here. And all along this curve, the slope of the direction field is equal to 1. The slope of the direction field is equal to 1. So I draw little line segments with slope 1. This is really hard to do when it's curving through space like this, but I'll try my best. Right? I've got positive 1 slope. Positive 1 slope. And if we increase to c equals 2, we see that it just pushes that line out a little bit. Right? So this is the c equals 2 isocline. And along this, the slopes are a little bit steeper. Right? They're a 2 slope instead of a 1 slope. Still positive, but positive 2 instead of positive 1. Okay, on the flip side, what happens if I pick c equals negative 1? Remember, this is the slope. Slope equals negative 1. Well, if I plug that into my isocline, I get y equals negative 5 over x. That's this guy. That's this guy. And along this curve, the slope is supposed to be negative 1. Negative 1. So now I have a negative slope. Negative slope, right? So the green curves in this picture are the isoclines. Right? They represent curves where the slope is the same. Curves where the slope is the same. Oh, that was kind of bad. curves where the slope is the same. And you can see how you would fill this out more and more, right? You could keep going forever. And you get all these nice curves where all the slopes are all the same along the curve. And if we go back up to our original picture that didn't have anything on it, you can still spot these isoclines, right? They're here, right? All the curves on this line have the same slope. All the curves on this line have the same slope, or they're supposed to, pretty close to it. Right, you can see down here, these are all like close to +1 slope, right? Or you go this way, right? Here's some more. These are all like -1 slopes. So these are the isoclines. This is the second way to draw a direction field. So the first way to draw a direction field is to just pick a bunch of random points, right? Pick some points in the plane and find the slope at that point. The second method of drawing a direction field is to use the method of isoclines. It's up to you which one you like. It doesn't really matter to me. Either way is fine. The homework's going to ask you to do both ways, and I think on the test I asked you to do both ways. I don't remember. Okay, last bit from this section. Phase portraits and autonomous differential equations. So sometimes the function on the left-hand side does not involve the independent variable. Sometimes your differential equation is dy dx equals a function of just y. In this case, we call these autonomous differential equations. Autonomous. And it's pretty easy to graph these because the slope of the solutions, right? The slope of the solutions only depends on the height of the function. Right? It only depends on the height of the function. So if we go back up to this example, right, the slope of the solution depended on both x and y. So by moving up and down, I change slopes, and by moving left and right, I change slopes. Excuse me. If we imagine that this is just a function of y, like if x was not there, then it wouldn't matter where I was left to right. It wouldn't matter where I was left to right. The slope of the solution would only depend on the height, right? So you could imagine that like you'd have isoclines that look like this, right? These would be your isoclines. Much nicer, much nicer. Let's look at an example. Oh, and the zeros of f play a really important role, right? These are the critical points. The zeros of f are the critical points. So here's an example. Again, it doesn't matter if you change p to y and t to x. You get the same thing, right? But we're just going to do it in terms of p and t because we'll see in a future section that population dynamics are often autonomous differential equations. And p stands for population and t stands for time usually. So this is like the population at time t. Population at time t. So here you go. Here's an autonomous differential equation for you. dp dt equals p times a minus bp. And notice that the t does not show up over here, right? No t's. No t's on the right-hand side. That means this is just a function of p, right? Just a function of p, which is my dependent variable. So this is autonomous. Autonomous. And we're just going to assume a and b are some positive constants. Whoops. Just going to assume that a and b are some positive constants. This is autonomous, since dp dt equals a function of p. And the critical points of this autonomous differential equation are the points where this function is 0. Right? These are the critical points. We're going to like draw vertical lines for these critical points because you'll see in the picture below. What are the critical points? Well, it's where this equals 0, and since this is a multiplication of two things, that means either the first thing equals 0 or the second term equals 0. Right, so we either get that p equals 0 or that a minus bp equals 0. And in the first case, p equals 0, we get this solution. And in the next case, a minus bp equals 0, we get p equals a over b. So these are my critical points of my autonomous differential equation. And then what do? Well, we break up the p interval, right? The p interval, p is going to be in negative infinity to infinity. We break that up. We break that up using the critical points. This is very similar to, let's think here, increasing and decreasing functions from calculus 1. If you wanted to find the intervals of where a function was increasing, where it was decreasing, etc., you'd do this kind of breaking up the interval by the critical points. So we take the interval negative infinity to infinity, and we break it up by these critical points, right? So there's a critical point at 0 and at a over b. So the first one, that since a and b are positive numbers, right? A and b are greater than 0. That means this a over b is also some positive number, bigger than 0. So we can break up the interval, right? Negative infinity to infinity, by first making a break at p equals 0. And then you go from 0 to a over b, and then you go from a over b to positive infinity. So we do that. We take the interval from negative infinity to 0, then we take the interval from 0 to a over b, and then we take the interval from a over b to infinity. And then we just find the sign of f. We find the sign of f on that interval. Right, so if p is between negative infinity and 0, then f of p is negative, right? Because this term will be negative and this term will be negative. Sorry, what am I saying? If this is less than 0, then p is negative, and this, a minus bp, is positive, sorry. So this is less than 0, and this is greater than 0, which means the whole thing is less than 0. Negative and a positive make a negative, right? So on this interval, if p is in here, right? P is in here, then f of p is negative, which means if f of p is negative, if this is less than 0, that means that the slope of the solution p is negative, which means p must be decreasing on this interval, right? And you can do a similar game where you pick p in this interval. You see that f of p must be positive, which means that dp dt is positive, which means that p of t, the actual solution, is increasing on this interval. Right, so you can do this for all the critical points, and you fill out this nice little table. And then from here we can draw the direction field pretty easily. How do we do that? We do it with what's called a phase portrait, right? And this is kind of broken up into two segments. You've got this phase line over here, and then you've got the phase portrait on the right-hand side, right? You've got the phase line on the left and the phase portrait on the right-hand side. What I usually do is I start out by drawing this phase line, and I draw this. And then on the phase line, I add in my critical points. Right, there was one critical point at 0, p equals 0. This is my p-axis. This is my p-axis. There was one critical point at p equals 0, and there was another at a over b. And I know on that line, p equals 0, I have a critical point where my slopes are 0. And on the line p equals a over b, I have a critical point where the slopes are 0. So I get these, I guess you'd call them asymptotes, right? I get these asymptotes. Now, I've already done the work here. I know that on the interval negative infinity to 0, f of p is negative, right? So I go on this negative infinity to 0 segment, right? Negative infinity to 0 segment, and I draw a little down arrow indicating that it's decreasing on this interval. Similarly, on this interval from 0 to a over b, right, on this interval, 0 to a over b, this p interval, I know that it's increasing, right? Increasing. So I draw a little arrow showing me it's increasing. And then the last one is also decreasing. And the idea is that if I pick a point P naught, like an initial population, think of this as like an initial population, I can see what's going to happen by just following this curve, right? It should be an increasing function. It should be an increasing function on this interval right here in the middle, right? In this little box, the function should be increasing. And it will not cross this asymptotic line. So if I imagine, my function is increasing along this, in this section, right? I have an increasing function of of t. Well, similarly, on this bottom section, right, I have a decreasing function that's kind of, it's coming from the asymptote and then is decreasing away. And similarly, up top, I have a decreasing function, but it can't cross this asymptotic line, right? Now, if we forget about everything over here, right, and just focus on this bit, right? This is kind of like population dynamics, right? This is what happens to populations. For different initial populations, you're going to have different behaviors, right? If your population starts too low, it's just going to die off, right? You'll have an extinction. If your population is in this Goldilocks zone, it will increase up to a maximum, right? Up to the maximum that the environment can handle. And if your population starts out too large, it will decrease to the limit of the environment, right? So there's like these like stable lines, right? This is like the extinction line, right? And this up here is like the equilibrium. These are like the equilibriums of the population. And if you're below the extinction threshold, then you're going to die out. If you're above the extinction threshold, you're either going to increase up to the equilibrium point or you're going to decrease down to the equilibrium point, depending on how high you are in your initial population. So these are kind of like the autonomous differential equation motivating examples. And again, we can see each of these red lines that I've drawn is a solution to this differential equation if it passes through this point P naught, right? So if I say that my population passes through this point P naught, then I can draw the solution curve, right? So again, we're doing solution curves without solutions. Okay, that's the end of this lesson.